Thank you so much. Yeah, we're a little bit over time, so we'll try to eke it back somehow. But next up we have, I'm very happy to hand over to Hannah Sargeant from the University of Leicester, and it's all about ISRU operations water extraction. So handing over to you.
Yes, hello everybody. Welcome to our session on ISO operations water extraction, and we are going to start off with Paul Zabel and Luca Kiewiet from the German Aerospace Center, DLR. Are they in the room? Yes.
Hello. We do this in 2 people, but that's not our presentation. Are you happy to go ahead? Yeah, we are.
Sorry, I do apologize. I had the order down wrong. Do you mind waiting for the next talk? Sure. Sorry, I'm doing a terrible job at chairing this session already, within 1 sentence down. I'd actually like to introduce Koorosh Araghi from NASA JSC with their talk on lunar and Mars water extraction technologies. Thank you.
Thanks, Hannah, and thanks for the introduction. Good afternoon. I'm Koorosh Araghi from NASA Johnson Space Center and Technology Manager for the center. So today, I'm going to give you the Moon to Mars ISRU water extraction technologies overview, and these are the technologies that JSN is known as providing eye charts, so welcome to another eye chart sessions. This is NASA's cultural things we provide eye charts. So this one is, you already seen this, Jerry has showed it from the ISRU, from the prospect and to product. We're focusing right now on the red box, which is a water extraction. Currently we have 2 missions, Prime 1 and Viper, as locating water sources on the moon, and ultimately from water mining we have invested on multiple projects, techniques, and currently I'm going to cover the ones that are TRF 4 to 5. Prime 1 is from the SMD Science Mission Directorate, and the Viper is from the STMD Space Technology Mission Directorate, and the goals for both of them are to determine where the water is. The first, one of the technology that we focused on, and this is a planetary surface independent. Originally we looked at it from the Mars application, and then we transitioned it to the lunar, the lunar auger dryer ISRU, known as LADY or LADY. It's based on an auger technology and is a continuous, one of the technologies that's continuous operations and is not a batch process. The concept of the operation is that you place the LADY in the PSR and with the excavator, and you bring the resources to the LADY and processes continuously, and then you have a water tank. You fill up the water tank, bring it up to the rim, and do the processing on the rim's surface. We looked at it with the KSC Razor that previously you have seen this, multiple presentations. There's a drum configurations, and then using a side sorting. And when the side sorting took place, LADY would process it, extract the water, condense it, put the water tank that Glenn Research Center works on, and transfer it to the rim and for the processes and doing the electrolysis to make hydrogen oxygen. So this is the process of the LADI. If you look at it, this is a very busy chart with a lot of images. So we looked at it from a state of, at the beginning, to use the plastic glass type of the casing to look at the mechanism and mechanic of the soil moving through the auger. This system uses the regolith as a plug mechanism, so the system does not have any isolation valve and operates below the triple points of the water and around 0.6, 0.7 psi pressure. After we characterize the design of it, we move to the actual casing, which is a stainless steel, did a thermal analysis to determine where to put the heaters on. These are strap heaters. If you look at the right-hand side pictures, it shows the casing with the strap heaters, and the location of where the water was coming out depends on your thermal profile. We look at the multiple design aspect and the modeling, and look at the lower case. You see the water is being condensed to the condenser and drops. The water was very clean, but it still has some particle in it. And obviously, that requires, as you learned from the experiment, when you're on the surface, even though you extract the water still has some contaminant in it as part of the particles. But at this point, this technology reached the TRL4, and we moved on since the direction of our mission changed to go after oxygen extraction. So this became the secondary, but this reached a TRL4, and we also did some experiment with for the Martian application as well. The next one is a PVAX, is a planetary volatile extraction. Work with the honeybee robotics. This based on a batch process, which means the drill core would drill below the subsurface to the icy regolith and heat up. The drill has its core that at the side heats up, and volatile comes up and extracts the volatiles, and you can store it in a kind of the balloon or expandable type of the system. So this test was completed, reached a TRL6, TRL4 and 5 and 6. Certain part of this device is sectioned of this drill at TRL6 because of the honeybee robotics fabricated drill for the Viper as well. So here the video shows how well the drill mechanism will start drilling through the icy regolith, and they demonstrated that they can extract the water from its core, and this is the result of that test. So what they did, they put add the water to the NULHT-2M, which was generated by formulation by JSC, the Geoscience Group, Geology Department. So with the 4%, 5%, and 6%, and it shows the speed of the drilling and the power required and how much water was extracted. Notice that the water in that glass jar at the bottom still has some particle. Even this method, we still detect some particle was still coming out. So let's shift now from lunar to Mars applications. And again, the two planetary has two different geological landscape. So on the Mars, we do where there is a good deposit of the ice below the surface. Geologists, they call it blue ice because you find the blue ice in South Pole or Antarctica, so they call it blue ice. The depth of this ice is pretty high, and it put it in perspective. So by knowing that that much water is there, we start looking at the Rodriguez well. Rodriguez well, or rod well, is a mechanism that allows for right now, Coral, which is a core engineering, Army engineering at South Pole, use this method to draw water from the usage and for the crew. So the concept is that you look at the subsurface water, the ice that is deposited, and try to draw that ice or water to generate the pool of water, and to try to dry it out. That's the concept of the Rodriguez well is. So this is if you look at the subsurface water, the way Army is doing it currently, they have it drilled to this first layer of the surface, get to the ice. They put the pump in there, they heat it up, generate the pool of water, they put heat in there, and as the pool is generated, and they just start drawing the water upward. And the same thing, they keep maintaining it with some level of the heat goes in to stays that pool of water in the liquid form. So the question is always been how would the human missions would take advantage of this abandoned the water. So number one is when you look at it from the propulsion standpoint, you can generate 20 tons of water plus CO2 to give you the oxygen you need and the methane for propulsion system. At the same time, the water is used for the human habitations, for usage, and also when using it, water electrolysis or water electrolysis plus the CO2 from the atmosphere. From the Sabatier, you can generate your methane, and that is your process to make the oxygen and fuel. So to put that one in perspective, obviously that was a study that was STMD, Space Technology Mission Directorate, funded to JSC, Geology, and the Science Department to investigate and do an investigation on the feasibility of the rod well and how it operates, and is it feasible to be for the Mars missions, and a study shows yes. So Honeybee Robotic took advantage of that rod well and come up with the Redwater project. Redwater project is based on using a JPL Athlete rover type, having a drill. The drill would penetrate through the surface, but the drill has its own, all these devices as the heating and generating the partial pressure to draw the water upward, and also using the bellows to seal the core to ensure they can pressurize the pool correctly to get the water out. This is a concept of the percussion type of the drill mechanism. It gives you the overview of where the water storage, they bring the water up, and currently in their CONOPS, they do the water cleanup and electrolysis on this same rover. And Athletes rover, if you are familiar with the Athletes rover is pretty large in size, and so it can accommodate providing all the processing system on the top of the rover. This again, I think I covered this, but that's described. Stage one is the pneumatic drilling to the required depth, and the step two is the boreholes, sealing, and the pressurization, melting of the wall, and then pressurize the wall and start pulling the water upward. One of the advantages is now it has been demonstrated. Unfortunately, I cannot play that video. If somebody can click the video on the right hand side, the IC. So this was also reached the 5, it shows, demonstrate that they actually did cut through the ice. They were able to generate the pool of water, and then they start drawing the water upward. And that's reached the TRL4, TRL5, and their Martian chamber. And they collect the water and then analyze the water. They try to mimic some of the volatiles in the water. One of the things we don't know at this point, if you go to the Mars surface, below the surface ice, how pure that water is. So that's something that ultimately we have to learn with the future missions. With that, I think I'm on time.
Great.
Sorry, I went very fast.
Thank you. So, thank you. Do we have any questions in the room? Yes, down here.
Okay, Robert Lindner, ESA. Thanks for the talk, very nice. Concerning getting the water out of your, let's say, well, have you considered any kind of issues with, for instance, gas inclusions, so pump priming, things like that?
Currently, when you look at it, from the Martian aspect of it, I think by heating up some of the water, when you seal the core, you can generate a partial pressure that you need by heating up. As you heat up your partial pressure, the wall allows it to partial pressure to push the water upward. Because of the low pressure, CO2 pressure in the atmosphere, it's going to be difficult to use the atmosphere as your gas pressurized in that tank, because of the nature of from the atmosphere pressure, that the 6 store is going to be pretty tough.
But your pump is self-priming if you get the water out, so you don't have an issue with having to prime the pump in order to have water in the system.
But ultimately, you have to still generate some heat to allow the rest of the wall to start becoming liquid. I understand what you're saying. What power put in there to start just pumping upward. Yeah.
So,
Thank you.
thanks.
Thank you very much. Could we now move on to our next speakers? And this time, I promise you, it is Paul Zabel and Luca Kiewiet from the German Aerospace Center, DLR.
Yes, so we are lucky we can be 2 times on the stage today. So my name is Paul, this is Luca. We both work for the DLR Institute for Space Systems in Bremen, and we are here to present our project LUVEX, which is about lunar water extraction and purification. This project is funded by the European Union, and as you see in the bottom of the slide, we have 5 other partners, and Luca and I are representing today a team of 25 to 30 engineers and researchers who work in this project all over Europe. The project started in November 2022 and it ends in October this year, so it's a quite fast-pacing project with only 2 years to build up a complete demonstration equipment for our experiments. Our goal is to show the complete water process chain from water extraction over liquefaction all the way through purification into a storage system. As typically for European-funded projects, we have a bunch of partners and all of them are doing what they can do best. So we at DLR, we focus on the water extraction and liquefaction part. We have the Technical University in Braunschweig who supports us with with icy regolith simulant and also with a thermal vacuum chamber where we carry out all of our experiments. Further down the process chain, we have Thales Alenia Space in Italy, who works on the water purification and water storage part. And we have Polish partners from Scanway and from Wrocław University of Science and Technology who work on the condition monitoring and quality monitoring of the water. And with this, I give over to Luca, who talks more about the water extraction liquefaction part.
Yes, thank you, Paul. Right, so I'm responsible for the extraction and capturing process for the LUIX project. As you can see on the image on your right, all our components, all our subsystems are actually in a TVAC. This is a TVAC in Braunschweig. I have a list with some of the stats of this vacuum chamber. So it's cryogenically cooled all the way around. We can go up to 100K Kelvin. The turbopump can go down to 10 to the minus 6 millibar. And just to give you an idea of the size of our system, the crucible there at the bottom has a diameter of 30 centimeters and a height of 30 centimeters. So that is more than enough volume for our IC regolith sample. And we want to go up to 15 kilogram then of IC regolith. For example, if we had a 5% weight percentage there, that would mean 750 milliliters of water that we could potentially extract. We also want to add other volatiles like CO2 and methanol in the ratios that they were detected by in L-Cross. So let's have a closer look at our crucible. On the picture on the right, you can see that we are actually currently integrating the whole system in Braunschweig right now. We hope that everything is done, let's say, mid-April, and then we have the first experiment results at the end of April. The 3D drawing in the middle is transparent, and there you can see 8 rods in the middle of the crucible. This is the rods that we will be heating and also stirring the isoregolith sample with to increase the effective thermal diffusivity then, because as most of you probably know, the thermal conductivity of regolith is rather poor, so we want to do everything we can to actually get more heat into that sample and sublimate the ice. We also simulate that, so here's a nice GIF of how that looks like. So by stirring, we effectively increase the volume that we can heat, and it helps also with distributing the heat around then. You can find some more details on this on the poster by Mart Heidkamp. So please do check that out. So when the ice is sublimating, up next is the cold trap. And in our cold trap, we have 2 cold fingers that we can both cool and heat, so we can accurately control the surface temperature. The idea is then that all the ice that is sublimating from the regolith sample travels or finds its way towards the cold trap, and it deposits again. And once it's there, because we control the temperature to roughly 190 Kelvin, we only capture the ice, or the water then, and not the other volatiles like methanol, for example. Once we have collected enough ice on our cold trap, we delaminate it, and it falls down through a slider into our liquefaction chamber. And in this liquefaction chamber, we have a sort of cup that is made of copper, and we can heat that. So we close the slider that is above it. We start heating. It's a contained environment within our system then, and we can actually liquefy the water, and then it can flow out of the vacuum chamber, and our colleagues from purification can take care of it, of which we'll have some more slides later. But first, some more words on the IC regolith simulant that we use. So the regolith simulant we use from Lunex Technologies in Berlin, and the ice particles, they are made by our colleagues in Braunschweig. And with this process that is here on screen, they are able to create incredibly small individual ice particles. And that then we mix this regolith and these ice particles together in a bath of liquid nitrogen to create an unfused, discrete IC regolith. The reason we want this kind of simulant is because there is not really any binding between the ice and the regolith, and therefore the heat conductivity is at its poorest. So if we can extract the ice successfully in this case, then it should be, if the ice is a bit fused with the regolith, it will always be better. So this is the worst case, essentially. Here are some photos of this process. On the bottom is the photos of how we mix this. As you can see, they are a bit fuzzy, and that's because we use a lot of liquid nitrogen, and that keeps evaporating as we go. So it's a bit gassy there. Yes, and then we also add the other volatiles during that process. If we do not use a lot of liquid nitrogen here, so if we try to cool down the sample first, then add the ice, we found that we create actually large ice clumps, and that we do not want to have. We want to make use of these incredibly small ice particles. Yeah. And with that, I give it back to Paul. Yeah. There you go.
One more thing to add, Luca forgot to tell you that for the icy regolith, we also have a poster by Henning Wache, so if you want to know more, you can also look on that poster. I'm now presenting on behalf of our partners at Thales Alenia Space in Italy for the water purification and storage subsystem. So the goal was to have a system that really has very, very low rate of consumables that are needed to purify the water. So the requirement here was to have less than 1 gram of consumables per kilogram of product water. And we wanted to have a feed ratio or product to feed water ratio of greater than 95% so that most of the water is really processed. And in terms of water quality, the requirement was to produce potable water, but also technical water for water electrolysis, which has even more severe restrictions on contaminants. Our colleagues in Italy then came up with this process chain. So we have first a microfiltration unit to remove any remaining regolith particles. As we heard in the previous speaker, you always get some regolith particles with your water. So the first step is to remove those. Then we have a reverse osmosis unit, which removes the majority of inorganic components, followed by activated carbon units for the organic contaminants. And then we have at the end an ion exchange resins unit to further polish the water to requirements coming from the technical water. This is how it looks like. So we have a cut drawing on the left and the actual hardware on the right. So it's like a little drawer thing that can process our water that we are extracting with our water extraction system. And it has, similar to modules on the ISS, it has all those docking points in front of the drawer. The colleagues in Italy have already done some tests to check out their hardware even before we do our big experiment campaign. So they used water that we artificially contaminated with regolith particles from the regolith simulant, but also with ammonia, with sulfur dioxide, with methanol, and a few other things. And they put that into their purification system to come to check out the hardware. And just a bunch of results. So you see that the orange-red line is always the upper limit, and you see that for things like EC and pH value, that all works fine. For TOC, which is mainly then the methanol part, we also stayed well below the limit, but there were some things that are quite close. So you see it's the methanol, if it's really as much as L-cross data is shown, might be a problem. We also do, as part of those European projects, a lot of outreach and dissemination activities. So you can follow our project on our website, on our LinkedIn accounts. We have a very nice podcast series, Water Beyond Earth, on Spotify, where you can hear people from the project explaining the project in the background, but we also have some famous names there like Angel Abud Madrid and James Carpenter also bringing in their perspective and their experience. So you can really check this out on Spotify. It's very nice to listen. We also have a couple of videocast mini-series on our website where you can see all the different people working in our project and explaining what they are doing. We have been at the Next Nature exhibition in the Netherlands with a poster and some samples. So there's many opportunities to follow our work and to get updates on the projects. And hopefully next year then we can present our hopefully very good experiment results. As Luca said, the next steps for us are that we finish integration hopefully by mid of April, then we do some preliminary testing of the hardware until end of April, and then we want to start with the first set of experiments and then gradually increasing, getting closer to the final test setup, which then would be really testing the complete process chain, so really running from inserting the icy regolith simulant in our experiment all the way to clean, pure water on the other side. And my personal hope is that at the end we have a couple of glasses of water that we can drink. That would be my goal personally. So thank you very much. And if you have questions, we are here. And we can probably also answer now a question, but we are also here at the conference. So next approach. One more slide. Oh, sorry. My bad, we have one more slide. So yeah, basically I already summarized that part a bit. So we hope to have our experiments and results by then summer this year, with all the evaluation of the results done in October. And hopefully with our project we then can contribute to future work in water extraction and water purification on the moon. So we hope that we can also find ways to further develop our hardware, which at the end of the project might be a TRL 4 to 5. And then we hope that in a medium-term outcome we can further develop the hardware with the long-term goal to one day be on a technology demonstration mission as part of the European efforts of lunar exploration. So now we are done.
Great, thank you so much both for that presentation. So we do actually have a question online to begin with from Brian Murphy. They say, great talk and thank you. Could this technology be adapted to specifically beneficiate the raw ices and regolith to extract solely higher order volatiles? Such resources are valuable for bioastronautics, experimentation, etc.
Yeah, so I did mention that we then also want to add methanol, for example, in our icy regolith sample. And indeed, I have some ideas on how you can use, for example, multiple series of cold traps to filter out specific volatiles. But it's only an idea so far. I think it should be possible, but let's see.
Are there any questions in the room? Down here, yes?
Koorosh from NASA. So thanks for the presentation. So you mentioned that you add in ice, not just mixing it with your regolith. One of the things, have you thought about to just add in water to your regolith homogeneously? Because when you do that, from the energy, that the other one maybe takes energy, but from the other way, which is normally you see on a lunar surface, right? The ice regolith is it's homogeneously, ice and regolith are mixed. When you do your water extractions, which is a batch process, and you freeze it, you still will see some particle transfer with that vapor that is coming out. So that's, we have experienced that. So maybe that's something to consider. The second part is methanol, yes, but have you looked at the other contaminant within the L-cross, which is mercury is one of them, and sulfide is the other ones. And how do you plan for clean those things out?
Yeah, do you want to go?
Yeah, with the that dust particles travel with the water vapor, we are pretty sure that this will happen. That's why we have the microfiltration unit at the very first step of the purification. We looked into other contaminants, basically everything that was measured by L-cross. The big problem that we faced is that when we want to put this in our icy regolith simulant, we face challenges with the thermal vacuum chamber, with the sealings, with the pumps, etc., not really liking all those contaminants. So we really had to reduce our ambitions there a little bit. But the water purification system itself should be capable of taking out those contaminants, but we have not tested this yet. But yeah.
Thank you.
Small addition. Also, methanol, its phase diagram is very similar to that of water. So in terms of cold trapping and trying to distill out the methanol, that was the hardest thing to do. So if we can achieve that, then the other volatiles should be not so much a problem.
Right, thank you very much. Okay, so now we will be moving on to our next speaker. Next we have James Cole from the Open University talking about water extraction from various icy regolith samples using low-power microwave heating.
Yep. Okay. Hello. My name is James Cole, and I was a PhD student at the Open University. So I've now finished. I handed in my thesis a couple of months ago. So hopefully the next time I speak to you, I'll be Dr. Cole, but we'll see. So for the last 3.5 years, I've been working on using microwaves to extract water from icy regolith. And today I'm going to talk to you about the final section of my work, which was working on various forms of icy regolith and using a bespoke instrument to measure the mass loss in real time. So, as has been mentioned various times already, water will be a useful resource on the moon. We want it for human habitation, for agriculture, for nourishment, but the most important point is we want it for rocket propellant, as it might sustain a cislunar economy that's worth billions. So it's one of the most useful resources we can get. The problem is that the water ice is stored in a particularly harsh location. You've got the vacuum conditions of the lunar environment. It's very cold. It can be as low as 40 Kelvin, and there's no sunlight. So what we need forms of getting this ice out as efficiently and as quickly as possible. We don't want anything to be staying in the PSR for as longer than it needs to be. And techniques need to be established that can efficiently do so. And as the two people before me have already mentioned, that there are many ways of doing this. Most employ thermal mining, so putting heat into the icy regolith to remove the water. We know from other experiments that microwave heating is very good at coupling with lunar simulant, at least at high temperatures. And so my PhD was looking into, well, why not use microwave heating for low temperature experiments? So at the Open University, we have a microwave heating unit. I'm sure some of you have seen this picture countless times. It can produce microwaves between 200 and 1,000 watts at 2.45 gigahertz. And it uses a standing wave regime to lead to areas with very high electric fields, which allow you to place the samples in those spots and get hot spots and then thermal runaway. The microwave heating unit is attached to a vacuum system, so we can go as low as 10 to the 5 millibar, and a mass spectrometer is also attached to analyze any volatiles that are being released. It's previously been used for sintering experiments, and so the initial part of my PhD was to adapt the system for water extraction, and that is the process described in my first paper, where I looked at the differences in extraction using different water contents and different mineralogy simulants. And initially what I would do is I would take the mass of the sample initially and the mass of the sample finally and draw a straight line between them and say this is how you lose the water. I quickly realized that's probably not the best way to do it, so over the last couple of years I've been working on something called the dynamic mass instrument, which can measure the mass of a sample in real time in the microwave environment. So how it works is a load cell, it measures the mass, but it is isolated from the microwave energy, so there's no interference going on. And then a load arm is used to go into the cavity which a sample is placed on top of, and that can be used to measure the mass in real time. So we can measure samples between 100 and 200 grams, their changing mass, I should say, with a resolution of plus or minus 0.1 grams. We have tested this in various ways. We've done various calibrations, including temperature and pressure calibrations, and that is in the details of my second paper. It's quite a gory paper. I wouldn't read it if you don't want to. So if you want to heat samples, you need samples. And what I wanted to do in this final section was look into how the extraction has changed by different forms of ice. Most of my experiments beforehand have been looking into diffuse ice, so where you add liquid water to a sample at room temperature and then you freeze it down. So the water is homogeneous and you sort of form a concrete. So what I changed this time is I also formed some granular ice, where I add ice particles to cold simulant, and then I cool it down further to 100 Kelvin. The grains were between 1.3 millimeters and 2.7 millimeters. So as in, we had one sample type with 1.3 millimeter grains and another sample type with 2.7 millimeter grains. Apart from that, all the samples were kept the same. So they had a sample mass of 40 grams. They used LHS1 as the simulant, and we aimed for a water content of 5 weight %. So as I said, the previous work had explored the previous work explored the impact of mineralogy and water content, and what I was looking at this time was the form of ice, so that was comparing the diffuse ice to the granular ice. I also, from the first paper, had seen that the surface area of the ice in the samples had an impact on the extraction. So I wanted to look into the surface area of the ice. With the diffuse ice, it's very difficult to gauge what the surface area of that sample is. So that's why I've got the two different grain size subsets, because I wanted to be able to easily quantify what the estimate of the surface area was. The samples were then placed in the microwave heating unit and heated for 60 minutes using 250 watt microwaves. I aim to use 250 watt microwaves in my experiments because I want to establish something that's within the realms of possibility of a rover lander platform within the next few years. You know, the system can go up to 1,000 watts, but that might not be feasible right now. And then I use the dynamic mass instrument to measure the mass loss over time. So, as you can see, the graph on the right, we've got the 3 different sample types. The 0 to 600 section is just where the pump down is beginning. So we pump down the system to about 3 millibar. That's all we can maintain when you've got a icy sample in there. And then between 600 seconds and 4,200 seconds, you've got where the microwave energy is on. And then after that, it's just a section where we leave the microwave energy off, and we just see there's no more changes to the mass occurring. The important thing to note here is that for the diffuse ice and the granular ice with smaller grains, the mass loss is fairly consistent. It starts losing mass when you turn the microwave energy on, and then it's got a nice, fairly straight line while it does so. The interesting thing is that the granular ice with the 2.7 millimeter grains, it loses ice in quite discrete sections. So about 1,000 seconds, you lose a large chunk, and then it stops losing mass. And then at about 2,000 seconds, again, a large chunk of the ice is lost fairly quickly before running out. And I think one thing I want to mention about this, although I'm looking into the changes in mass, in detail for all these sample types, the main thing to note is that the microwave's going to extract over 80% of the water in 60 minutes with an energy efficiency of roughly 8 milligrams per watt hour. Now, another paper I've seen puts solar sintering at about 10 milligram per watt hour. But the thing with microwave heating that might put it over the top and compared to solar sintering is that microwave heating only improves with scale, and these are very small samples. So if we could build a bigger system with bigger sample types, then the efficiency should improve from there. So, as I said, the main thing I was looking into was what are the differences in extraction for the different forms of ice, and what we found was for the forms of ice, for the diffuse ice compared to the granular ice with the 1.3 millimeter grains, no real differences. But then if you compare it to the 2.7 millimeter grains, there is a big difference. And that can be quite easily explained. With the 2.7 millimeter grains, the first drop in mass that you see is probably the ice grains that lie on top of the sample, and then are extracted quite quickly when the microwave energy is turned on, because they're then also exposed to the vacuum of the system. From there, you have to then wait a while before the temperature in the core of the sample increases. However, the big drop in mass occurs because the individual grains are larger. So once they get to a high enough temperature, your vapor that's in those grains, the vapor pressure is quite high, and it pushes forward with a higher pressure, and therefore your water mobility is increased. It's also why you're probably seeing that the granular ice with a 1.3 millimeter grain is lower, is in terms of the extraction. The smaller chunks of the 1.3 millimeter grains act more like a diffuse ice because it's more homogeneous across a sample. And so that's why those two lines seem to be fairly similar. I think, firstly, this highlights the power of the dynamic mass instrument, and before this, we weren't able to see what was occurring within the microwave heating time allotment, and now we can see what's going on. So that was nice to see that it was a worthwhile endeavor. And I think it also shows that there's something to be said for extraction experiments also sort of as a cycle can almost act as a prospecting technique, where the mass loss can tell you what sample type you may have. With enough lab time and with enough variations in your sample type, you may be able to send something like this to the lunar surface and tell you, whether it be through mass loss or pressure increases, what you're actually extracting at the same time as extracting it. So you can aid yourself in both space resources, but also the lunar science that's going on at the same time. So I think that's, So in summary, microwave heating is actually quite an efficient technique for extracting water. And it can be further improved with a dedicated system. This system is meant for sintering. So if we could build a system that's meant for water extraction, not only could we get better efficiency, we could build in sort of a cold trap system like the Luvex system. And then we could also see how the scale improves with bigger samples, because we've always been limited to what the size of the cavity is. We've seen that different ices have different extraction profiles, and we could explore this further with further sample types, whether that be different grain sizes or using frosty ices or whatever forms of ice we can think may be possible. And that this work can take on further roles when prospecting data sets begin to come back. When Prime 1 or Viper, whenever they tell us what the form of ice is, we can use that to, in the microwave heating unit, to say what it might look like if it was heated up. And I've focused on low power. The system can only produce one frequency, which is quite an important thing because the frequency is really, really important for determining the depth of your penetration and also how much power you're putting in at any one point. So if we could build systems where you could change the power, you can change the frequency, and maybe add susceptors, but that's maybe more in the future, we could also improve the efficiency even further. I finished a bit early, but I think that's an okay thing. Okay, thank you.
Okay, great job, thank you. Are there any questions in the room? Just in case there's anyone else. Oh, at the back? Right in the middle? Where's the mic? Could the mic go to the back, please? Yeah, no, I'm just trying to distribute questions.
Thank you very much for the presentation. It was great, James. So I'm Vibha from ISRU. I understand the 250-watt microwave power. I think at the summary you touched upon the variable power concept. So 250-watt microwave power was enough for your small size samples to extract almost 80% of water in 60 minutes. Do you think when you scale up, when you work with bigger samples, you would like to play with the power, and that would help in increasing the efficiency of the final output?
I think I did some thermal modeling as part of my thesis, and what I found was that increasing the power at a certain point becomes, it doesn't add any more because you get to such a high temperature so quickly that your water starts sublimating almost immediately. So there's probably a limit on how much higher you can raise the power. You can definitely raise it higher than 250 and improve the yield. But I think still 250 has more capabilities with a higher scale of sample. I think there's still more to be tapped there in terms of what's possible.
Thank you.
Thanks. Okay, and then I believe there was a question down here. Yep.
Yeah, this is Matthias Spur from DLR in Cologne. I'm a little puzzled by the general summary that you say microwave heating of ice is efficient. So anyone who has molten chocolate or ice in the kitchen microwave would disagree. So first, a technical question. Do you have a record of your temperature in the sample? And then I would wonder also about the chocolate heating. You have a certain wavelength. You have a standing wave. And also what you basically seem to have is that you're heating the sample in general, and then the overall heat is melting the ice. So you're not attacking the water directly. Is that correct?
That is correct, yeah. So at 2.45 gigahertz, you're not efficiently heating solid ice. It's more aimed for heating liquid water. So yeah, what I meant more by efficiently heating was it efficiently heats the simulant around it that then probably is what's going on to heat the ice. Remind me what the first part of your question was?
You have a record of the temperature in the sample.
Yeah, so the microwave heating unit has pyrometers on it. So we have surface temperatures, but we do not have core temperatures. So that would require something like I can't exactly remember what they're called, but the RF probes that you can put into the core that the microwaves don't interact with. So yeah.
If we can make it a nice quick question, go ahead.
Actually, it's more like a comment that I think all the systems folks that they work on the water extraction, when you look at the perspective of real ISRU missions that looking at the pilot plant, extracting the 1 metric ton of water or the full scale of 10 metric tons or higher, from scalability and practicality of it. I think it would be good to look at that from that perspective beyond a laboratory and for the longer vision from a scalability, what the system look like, right? So those are, I think it's always, we do the same thing to our contractor or projects to put that one in perspective from the starting point to look at the future, how the system scales up, is the practicality of it, energy, and all that. Just was a comment.
Great. Okay, thank you. Can we please thank all of our speakers from this session?